Hello everyone, my name is J1. I'm very glad to be here to present our work WizMap, explore and interpret large embeddings in your browser. So over the past few years, we have seen a booming of large pre-trained models, and those models have incredible capabilities, and sometimes people also use them to track embeddings, and use the embedding of input data to some diverse downstream tasks. So for example, take the most classical example, like the bird model as example. So if we give an input sentence like the minions having a lightsaber duel with the minions, and the input sentence feed into the bird model, we can activate different layers, and we can also track the activation of certain layer as embedding of the input sentence. And those embedding can be interpreted as internal latent representation of the sentence inside of those pre-trained models. And those embedding can capture some semantic or syntactic meaning of the input sentence. And the output would be a vector. For example, here we have one vector with the length 768. So you can think it's high dimensional representation of the input sentence. And people can also track the embeddings from other modality like images. For example, for the clip model, they support different modality, including text and also images. So here the text with the syntax, and for the image, we use the image generated by Stable Diffusion. So using the text sentence as a prompt, we generate one image. So we can, from human beings, we can see those two input have very similar semantic meanings, both meaning minion having a lightsaber duel with each other, and also we expect the embedding to be very similar to each other because they encode the same semantic meanings. So after having the embedding of the different input data, people can do a bunch of diverse downstream tasks, such as classification, searching documents, searching images, and also people use the embedding, trying to visualize embeddings and do some clustering and also topic modeling. And in fact, visualizing embeddings is becoming a very, very common practice across different domains. For example, here some researchers use the embedding of the molecules in the high-dimensional embedding and use a dimensional reduction technique called UMap to map them, project them into a 2D space, so they can visualize them using scatter plot. So here they also label them to see different molecules families. They find out the embedding really can capture the meanings of the molecules. For example, molecules close to each other, they're also close to each other in the embedding space. Similarly, in social science, people also use embedding plus UMap or the dimensional reduction technique to visualize or make sense of different social media content. For example, here the researcher is visualizing the comments from different Reddit communities. And of course, in machine learning areas, people also use embeddings and UMap to make sense of large text dataset. For example, here, this paper, the researchers use the text people use to attack large language models and to see how people come up with different strategies to red team or attack large language models to provoke them to do something bad. And here, more interestingly, the researchers also manually annotate the different neighborhoods of the different embeddings in the lower dimensions. For example, they go through the different embeddings one by one to make sense of different neighborhoods, and they circle around those interesting neighborhoods and also add a label to communicate the different region with some different interesting topics around different neighborhoods. As you can see, going to annotating itself is a very, very time-consuming process. It can require you to go to a bunch of different data points and make sense of different neighborhoods. And in fact, there are many main points for visualizing embeddings. For example, the first one we mentioned interpretability, so I have to make sure we understand what the different neighborhoods means in the embedding space. And also scalability is a challenge as well. So as data sets become larger, it's very hard to visualize maybe 1 million data points. It takes time, and with 1 million data sets, it's very hard to implement interactivity. So how do you zoom in, how do you pan to see different neighborhoods become very, very challenging. And trying to tackle those challenges, we have seen some related embedding visualization tools have been developed over the recent years. And however, none of those tools reach to tackle all the 3 pinpoints. And trying to join the body of visualization tools and trying to visualize embeddings, we designed and developed WizMap, so which is open source visualization tool trying to visualize large embeddings and also help users to make sense of different neighborhoods in the embedding across different resolution. And WizMap is open source, and we have online demo, so you can click the link on the top panel to see the link in your browser, to see the WizMap in your browser. And right now, we're going to give a demo for WizMap. The first demo will use ACL abstracts. So for these datasets, we include 64,000 ACL paper abstracts. So the text or the sentences or the one paragraph for each paper. And those the abstract come from 1980 to 2021. And we use a mini LM to extract embeddings. So I think also 700 dimensions. And also use UMap to project them into a 2D space so we can visualize them using scatterplot. You can visit the link below to see the demo in your browser live. And right now we'll give a demo for WizMap on the ACL abstract demo and dataset. So when users open WizMap, they can see an embedding in the middle of their tool, and also there is some buttons on the top, also a search bar on the top left. So user can pan and zoom to see different neighborhoods, different regions of the plots. For example, and each blue dot is a paper, including title and abstract. User can hover over to read more detail about the particular data points. User can also click the plus and minus button to zoom in and zoom out, or click the home button to zoom to original scale. So you can also see there is some background behind the dot, so which encodes the density of different regions. So use the contour plot to encode the densities. User can turn off the point to focus on the density plot. For example, here you can see the contour of different density across a different data point in that embedding space. You can also only focus on points if they prefer that. You can also zoom in, zoom out to see hover over to read the paper abstracts and also paper title as well. And user can also turn on the grid mode to see the different topic of different grids. So by default, we highlight 20 interesting labels of different regions. The user can turn on to see more. User can, when user zoom in, or you can have like smaller regions, user can hover over different grid rectangle square to see the topic of a different square. So that encodes like the topics of the data points that fall into that particular square. For example, here we're looking at like a cyberbullying or hate speech, paper about hate speech, the cluster. So indeed, like many papers have talking about this hate speech, they're all captured by the topic automatically generated by WizMap. And user can also use a time button to see the resolution of different changes of the embedding space. So here we're playing animation to show like how the embedding changes over time. User can also manually drag the slider to see how the embedding. For example, over like early years, there are many grammar and parsing papers in ACL, and in probably 1996, there are more translation papers in the darker region, and around 2010, 2007, so I will see more like word ambiguity papers. And in recent years, there are more papers on question answering and also hate speech detection, classification. So that's about the time slider, and user can also use the search bar on top left to search different keywords. So for example, here I search hate speech, so we highlight like all the sentences, like, including with the abstract with the hate speech, so they can see they form clustering in that specific region. We can also search different things like translation. So here indeed the translation also form one cluster like on the other side of the embedding space. User can hover over to read more about the abstracts. WizMap is very scalable and can scale to millions of data points. And to showcase scalability with WizMap on DiffusionDB, DiffusionDB is a large data set of 14 million image prompt pairs. So those prompts are from Stable Diffusion users write different sentences to describe the images, then use Stable Diffusion to generate the images. And in this case, we sample like 1.8 million unique prompts. Also have 1.8 million images corresponding to each prompt. And we use clip embeddings to generate the embedding for the both like prompts and images, so in the same embedding space. Then we use the UMap to project them into the same 2D space. So when users open the tool, they can see a very similar layout as ACL abstract for WizMap. So we also have the different like labels with other summaries of different neighborhoods automatically generated by WizMap. So similarly, user can hover over different points. So here the blue points means prompts. So user can hover over different prompts to read the sentences. So here we have 1.8 million prompts. The user zoom in, zoom out is very smooth. So there's no lag. User can very scalably and smoothly transition, hover over different points to read about different prompts, different neighborhoods. You can also see different regions. For example, here users are focusing on the art regions. So here you can see the prompt have a very similar structure, as like a portrait of different objects, and also in particular artistic styles. And the user can also increase like the automatic labeling, so when showing more summaries of different more neighborhoods to help the user to guide through to navigate into the embedding space. For example, here we're looking at a photo like clustering, so maybe there are some different photos where you see when user zoom in, the square becomes smaller and smaller, so we're changing the resolution of images as the user zoom in, so we provide multi-resolution summaries across the different embeddings. And in DiffusionDB, we not only have prompts, we have images. So user can click the point drop-down menu to also show the images. So here we have like 1.8 million prompts and 1.8 million images. The red point means the images. So user can hover over the points to see the images as well. So user can see the different prompts and also different images. So here's all the embedding with some fantasy like objects or fantasy like generation. Here's more about a portrait. So we have more about like maybe the face of different people or the face building like characters. So we have like in the portrait cluster. The user can also turn off the points, so you can see there's overlap of different two embedding space. So one interesting thing about Stable Diffusion is like we respect the embedding of like the prompts and images to be the same space. So we expect them to overlap very perfectly. However, Stable Diffusion is not perfect, so again there's some mismatch between the different two embeddings, and also use the mismatch between two different embeddings to get a more idea like what's wrong in the DiffusionDB like data set. And here we can turn back to see the prompts. We also search different prompts. So for example, cat, you can see all the cat surrounding in the realistic photo categories. So here about trying to people generate real images, like real images about real objects. For movie cluster, so we have a large cluster about all the movies. So about painting cluster is more scattered. So you can see there are different like painting across different regions in the embedding space. So that's like the demo for with WizMap on DiffusionDB. And when I talk about some methods, like the build time constraint, where highlight some different implementation and design strategies we use to make the WizMap work across different the data sets. For example, WizMap is very scalable. It can scale like 3 million data points. And to do that with WebGL to render million data points, WebGL uses the GPU power on your machines. They can render a large number of data points. We also use the Streams API to stream large data source. Because loading a large data source can take a long time. So we just render them one by one, when during the streaming process, also render the data points already loaded into the memory, so you can have a smoother experience. We also use the web worker to parallelize the drawing, searching interaction, so everything is smooth. You can see when you use the zooming, everything is smooth. While changing the resolution of different grades, when different summaries, you can hover over different points. Also, everything is very smooth. But we use the web workers to parallelize the different functionalities. And you may be curious how do we generate those summaries. So in the paper, we also discuss more in detail about our novel idea of using quadtree partition to generate summaries. So the idea of quadtrees is we partition the space into different four thin-sized squares, and we recursively partition it into four squares. So we have a tree representation from the high level of space to the very low levels, the smaller squares. And then we propose a TTF-IDF score, which is tile-based TF-IDF score. So we compare the sentences for into one square across different square in that level to use TF-IDF score to surface the most interesting topic or the keywords of that tile, and with the top 4 keywords as a summary of that tile. Then we record the tiles, so when users zoom in, we can see more appropriate size of the square and to surface the topics of that square. So that's how we do the multi-resolution aggregation or the multi-resolution summaries of the embeddings. To learn more details, please read our paper to have more discussion on how we implement the multi-resolution embedding summary. And we also implement WizMap as usability in mind. So WizMap is portable, shareable, and easy to use. So we use a technique called Nova to implement WizMap. So user can use WizMap in different computational notebooks, like Jupyter Lab, Jupyter Notebooks, with Colab, with VS Colab. So everything is similar to that browser version. User can hover over to search, and user can also share the different WizMaps with the URLs. So after having some JSON files, user can include JSON file into the URLs. So you can share the URL to the collaborators. So if the collaborators click the URL, they can see the exact thing WizMaps. So it's very good for collaborations. And also, we create a Python library called WizMap, so user can use the WizMap Python library to generate their own WizMap with only 3 function calls. So we make it very easy for user to use the WizMap on their own data set. And that's all about the WizMap, and thank you for your attention. And if you have more questions, please reach out to us. You also read our papers, and also please try out a demo. So we have a demo link again here. And also, our code is open source. You can also try out the code, or maybe have some different feedback, or maybe you want to fix some bugs. You can also feel free to contribute. All right, thank you so much.